Today we're going to talk about Module 12, IPv6 addressing. So one of the biggest needs for IP6 is that IP version 4 is running out and has actually supposedly run out a few years ago. It is the successor to IP version 4, and yes, there was an IP version 5 which never made it to the docket, but they did work on it. And so they skipped the implementation of IP5 and went right to IP version 6. So it has a much larger 128-bit address space. The development of 6 also included fixes for IP4 limitations and other enhancements. So with an increase in internet population, a limited IP4 address space, issues with NATing, and the Internet of Things, the time has come to begin the transition to IP6. So again, in the depiction here, you can see the actual exhaustion dates of IP4 within each one of those registries. So IP4 and IP6 do currently coexist in most situations. Not everybody can just transition completely to IPv6. So they will coexist in the near future, and the transition will take several years. The IETF has created various protocols and tools to help network administrators to mitigate their networks to IPv6. So these migration techniques can be divided into 3 different categories. First category is what we call dual stacking. This is very popular. You'll see it in the lab when you do your IP config in your command prompt for your devices. It is simply running both IP4 and IP6 simultaneously on your end devices. Next is tunneling. Tunneling, and you'll talk more about tunneling when you get to Cisco 3, but tunneling itself is the process of transporting an IPv6 packet over an IP4 network. So the IPv6 packet is actually encapsulated inside an IP4 packet, making it look like an IP4 packet for all the older technologies utilizing IP4. And lastly is, again, translation. So Network Address Translation 64, or NAT64, is going to allow IP version 6 enabled devices to communicate with IPv4 enabled devices using a translations technique similar to NATing for IP4. So again, NATing for IP4 or IP6 was never ever intended to be the end-all be-all, the end solution. These were just temporary steps to take before you could migrate completely into IPv6. So tunneling and translation are for transitioning to native IPv6 and should only be used where needed. The goal should be native IPv6 communications from source to destination. Now, again, they are 128 bits in length and they are written in hexadecimal. They are not case sensitive and they can be written in either lowercase or uppercase. The preferred format for writing an IPv6 is using X's that indicate the hextet separated by a colon. So each X is going to consist of 4 hexadecimal values. So in IP6, a hextet is the official term used to refer to a segment of 16 bits or 4 hexadecimal values. So 4 hexadecimal values times 4 bits each gives you your 16 bits. Your 16 bits times 8 hextets gives you your 124 bits of information. So below here, you can see 2 different examples of an IP address. Okay, so 2001 double colon 0, colon 0 dB, 8 colon all zeros, colon, and then all ones, and then colon all zeros, colon or zeros, colon or zeros, colon 0 to 100. This is what we call a decompressed version. So as we continue on, there are ways that we can compress it to make it easier for us in the human network. So the very first rule to help reduce the notation of an IPv6 address is to omit any leading zeros. So in the examples here, 01AB can simply be represented as 1AB. 09F0 can be represented as 0F0. 0A00 can be represented as A00. And 00AB can simply be represented as AB. Be careful. This rule only applies to leading zeros, not trailing zeros. If I were to change anything after the 9F0, I change the value of that number. Or A00, if I change anything after that, then I am changing the value of that number. So only leading zeros. So down below, you see the preferred method, which is all of the hexadecimal digits written out, and then your first rule for compression. So this is compression rules. Is to get rid of those leading zeros. And your resulting is a little shorter than having to write out the whole thing. And you'll see that represented here with the no leading zeros line. Now, your second rule is a double colon can replace any single contiguous string of one or more 16-bit hex tets. So in the first example, the representation of the first is getting rid of the leading zeros. Next, the double colon, be very careful, again, can only be used once within your address. If you use it more than once, your device gets confused, okay, and does not know what to do with that. So you can only use it once. So again, your preferred method is the decompressed. I get rid of my leading zeros. I do not touch trailing zeros. Lastly, I choose where in the compressed address do I want to compress it more by using that double colon. Understanding double colon can only be used once. So my best case scenario, I'm not going to do anything with the first octet, the third hextet, because it's only one series of zeros. I want contiguous, like you see in 5, 6, and 7. That is where I want to truncate or compress. So if you have an address, let's say, so now the choice becomes, where would that double colon be more beneficial to you? Okay, if I were to put a double colon in the first series, that would be one option, or I could do it in the second series. That is another option. So what you want to decide is how many of those hextets can you compress? So for this example, my best bet would be compressing the last. Only once. You cannot do the following. Okay? You could not do that last way. Your device doesn't know. Do you have a series? Now, it knows it needs 8 hextets, but is the first double colon 3 and the second one 2? Or is the first double colon 2 and the second one 3? It does not know. So you can only use this rule one time. Now, there are 3 broad categories of IPv6 addresses. Unicast, again, uniquely identifies an interface on an IPv6 enabled device. Multicast is used to send a single IPv6 packet to multiple destinations. And an Anycast, this one is new within IPv6. So in IPv6, there is no broadcasting. No broadcast address that is being utilized. A packet is sent to an Anycast address, which is routed to the nearest device having that address. So as an example, in an Anycast situation, if I have multiple DHCP servers in my network, I can send an anycast out, which is a DHCP question, and it will go, or has the possibility to go to multiple different servers, but only the server that is closest will answer that request. There is an IPv6 all nodes multicast address that is essentially giving the same result as a broadcast. And we'll talk a little bit more about that. So the dynamic of your IP6 address. What used to be your subnet mask is now referred to as your prefix length. So it is represented still in / notation, and it is used still to indicate the network portion of an IPv6 address. It can range from 0 to 128. The recommended length for LANs and most other types of networks is a /64. So as you see here, they have taken and split the 128 bits right in half. The first 64 identify the prefix or the network. The last 64 identify the interface ID in IP6, which is the host address in IP4. Unlike IP4 devices that only have a single address, IP6 addresses typically have 2 unique addresses. Okay? Global unicast to GUA. This is similar to a public IP4 address. These are globally unique, internet routable addresses. Then you have your link local address, your LLA. This is required for every IPv6 enabled device and is used to communicate with other devices on the same local link. LLAs are not routable and are configured to a single link. Then pay attention to the definition as they break them out over here on the right. Your loopback address now is :1 with the prefix of 128. An unspecified address is :1 also with the 128. Unique local addresses are FC00 :7 to FDFF :7. So, an IPv6 unique local address is a range from FC00 :7 to FDFF :7. So this is similar to the private addressing scheme of RF 1918. There are some significant differences, however. Unique local addresses are used for local addressing within a site or between a limited number of sites. They can be used for devices that will never need to access another network. Unique local addresses are not globally routed or translated to a global IPv6. Many sites will use the private nature of 1918 to attempt to secure or hide their network from potential security risks. This was never the intended use of the ULA. So, your global unicast address. Again, globally unique, routable on the IPv6 internet. Currently, only GUAs with the first 3 bits of 001, which translate to 2000 :3, are being assigned. So look at that right there. Only the first 3 bits of that unidecillion address space is being utilized right now. Currently available GUAs begin with a .2 or a 3. This is only 1/8 of the total available IPv6 address space. So the way that it is broken out or broken down, if we are going to subnet, okay? And again, when you're trying to figure out where your 2000 comes from, and where this number comes from, you're simply doing conversions. Okay? You do your conversions. If I take my 4 bits down, right? What does my bit become? There's your 2000 right there. Likewise with the bottom. And there is your 3F. Okay, so when you're trying to understand these numbers, don't forget your conversion tactics. Okay, so that is your address range. Now up top you're going to see your global routing prefix, and you can see just that little portion currently is being utilized. This tiny little portion of the entire IP addressing scheme. So again, global routing prefix is the same as your network address in IP4. Your subnet ID is the same as the subnet in IP4. And your internet interface, or interface ID is the same as your host address in IPv4. Now, global routing prefix. The global routing prefix is the prefix or network portion of the address that is assigned by the provider, such as an ISP, to a customer or to a site. The global routing prefix will vary depending on ISP policies. The subnet ID is the area between the global routing prefix and the interface ID, and it is used by an organization to identify subnets within its site. So subnetting in the IPv6 world will always take place in the 4th hextet and go from there. Now, the interface ID is equivalent to the host portion of your IP4 address. It is strongly recommended that in most cases you use a /64 subnet. That is going to create a 64-bit interface ID. Now, a note here. In IP6, they do allow the all zeros and the all ones host addresses, which can be assigned to a device. The all zeros address is reserved as a subnet router anycast address and should be assigned only to routers. Even though it is allowed, it is typically not recommended that you do this. You want to keep it as simple as possible. When you have so many other addresses to choose from, why would you bother trying to make it more confusing than what it could be? Now, an IPv6 link local address enables a device to communicate with other IPv6 enabled devices on the same link and only on that link or subnet. Packets with a source or destination LLA cannot be routed. Every IPv6 enabled network interface must have an LLA. If an LLA is not configured manually on an interface by us, the administrators, then the device will automatically create one. The ranges are from FE80 : with a prefix of 10 range. So your routers will use the LLA of neighbor routers to send routing updates, and the hosts will use the LLA of a local router as their default gateway. So a little different in IPv6. Most of the configurations and verification commands in Cisco's iOS are similar to IPv4. In many cases, the only difference is the use of IPv6 in place of IP within the command itself. The command to configure an IPv6 GUA on an interface is IPv6 address is your command. Then be careful here. In IP4, you need the subnet mask along with the IP address. In IPv6, you need the IPv6 address along with the prefix, as you see here. Again, you issue your no shut, your device comes on, and a route is populated into the IPv6 enabled router. Manual configuration is the same. So when you manually configure the IPv6 address on a host, it is similar to configuring the IP4 address on the host as well. Only difference when you go into, you right-click on your Ethernet, you look for IP4, you say properties, you're going to scroll a little bit further down and pick IP6, hit properties, and here you're going to put in the IPv6 address, the subnet mask, or excuse me, subnet prefix length, and then a default gateway that you define or that will be manually assigned. If you do not assign one, the router will manually assign one because it needs it in IPv6. When DHCP v6 or SLAC is used, the LLA of the router will automatically be specified as the default gateway address. So configuring the LLA manually will let you create an address that is recognizable and easier to remember. So rather than getting that very long string of an LLA assigned by the router, I can go in and use, again, IPv6 address as my command and enter the IPv link local address. So in this case, FE80 : 1:1:1, and I have to specify that it is the link local. In my command, in order for the command to be understood. If you forget that link local at the end of this, your router will not know. Your router will give you an error. The same LLA, incidentally, can be configured on each link as long as it is unique to that link. Common practice is to create a different LLA on each interface of the router to make it easy to identify the router and the specific interface. So, as this example here. So while it is not necessary to do this step, you certainly could to identify even further just by looking at configurations where these devices live. Your devices. So we talked a little bit about these RS and RA messages already in our previous slide before IP4. They are used in the Internet Control Message Protocol version 6 for ICMP version 6. So your router solicitation or your RS message are sent by host devices to discover IPv6 routers. So now what we're going to find within the realm of IPv6, if I tell my router with a simple command to act as an IPv6 router, it now has the capability of handing out configurations to all other IPv6 enabled devices. Your router advertisements, your RA messages, are sent by the routers to inform the host on how to obtain an IPv6 GUA and provide useful network information, such as the network prefix and the prefix length, the default gateway address, the DNS address and domain name. The RA can also provide 3 methods for configuring an IPv6 GUA. Now these 3 different methods, Slack, the first one is the default. The other 2 are choices of the admin within the organization. And we're going to break those down. So Slack, SLACC, stands for Stateless Address Auto Configuration. Okay, so it allows the device to configure a GUA without the services of a DHCP version 6 server. It is the default method. After that, devices will obtain the necessary information to configure a GUA from the ICMP v6 RA messages of the local router. The prefix is provided by the RA, and the device uses either EUI64 or random generation or the random generation method to create its own interface ID. So the first part of your address is created from the RA message. The second part of the address is either using a process which is called EUI64 or a random 64-bit number. So your second method is Slack and stateless DHCP. So an RA can instruct a device to use both Slack and stateless DHCP v6. It will suggest the devices do the following. Use the Slack portion to create your own IPv GUA. The router LLA, which is the RA source IPv6 address, as the default way. And for all the other information, such as DNS and all that other stuff, use the stateless DHCP version 6 server to obtain that information. So this is the second method that you could choose. And again, in order for this method to happen, you have to go into your router and tell it to act as an, an IPv6 router. So once you do that, you're going to use Slack to generate the GUA. You're going to use the router who is acting as the DHCC server. You're going to use their default address, as the default gateway. And then if you need a DNS server or a domain name, you're going to get that from the server itself. And then lastly is method 3, which is stateful DHCP. So an RA can instruct a device to use stateful DHCP only, which is similar to DHCP for IP4. A device can automatically receive a GUA, a prefix length, and the address of DNS servers from a DHCP v6 server. The RA message suggests the router LLA, which is the RA source IPv6 address for the default gateway, a stateful server to obtain a GUA DNS server address, a domain name, and other necessary information. So again, first method, using Slack, having the router do its thing. Second method, getting the configuration information from the router and other pertinent information from the server. And then the third way, getting everything from the server. Now these processes here, this is how in IPv6 a device is going to get its interface ID. There are two different methods. When the RA message is either Slack or Slack with stateless, the client must generate its own interface ID. The interface ID can be created using either the EUI64 process or by randomly generating a 64-bit number. So the IEEE has defined the Extended Unique Identifier, the EUI, or modified EUI64 process, which performs the following. It will take the device's 48-bit MAC address, and it will insert into the middle of that address FFFE. It will also take the 7th bit of the client MAC address and reverse it from binary 0 to binary 1. So as an example here, it is going to become, as you see here, it's going to go from FC:99:47 to FE:99:47:FFFE. So those are your two delineating things to pay attention to when you are asked in a visual what type or what method was used to create the interface ID number of a particular device. So please understand that within here, there is a 7th bit. Okay? There is a 7th bit within here if I were to break this down to binary. Would we all agree? Yes, we would. That 7th bit is going to be a 0. That 0 would be flipped, which would give you a new parameter. Then you're going to insert FFFE into the middle, and this now becomes the interface ID. That is the EUI64 process, easily understood because of that FFFE. So even if you didn't know what the previous or original MAC address was, the only way to identify it would be FFFE tells me it was the EUI64 process. So again, depending upon the operating system, so it's dependent from the operating system, a device may use a randomly generated interface ID instead of using the MAC address and the EUI64 process. So beginning with Windows Vista, Windows uses a randomly generated interface ID instead of one created with the EUI64. Okay, understand, if somebody understands the process of EUI64 and they look at an interface ID and all they do is reverse the process, they remove the FFFE, they take the 7th bit and change it back to a 0, they have your information. So Windows has decided with Vista going forward that instead of using that EUI64, we're just going to randomly generate an address. So to ensure the uniqueness of any IPv6 unicast address, the client may also use a process known as duplicate address detection, or DAD. This is similar to an ARP request for its own address. If there is no reply, then the address is unique. So what happens is your device, after obtaining an IPv6 address, will send out a message, this DAD message, throughout the internet, throughout the network. And inside that message is who it's intended for. So if they get a reply back from that DAD request, then they can't utilize that IPv6 address because it belongs to somebody else. If they do not get a response, then they consider it a valid address and they take it upon themselves to address themselves with that address. So all IPv6 interfaces must have that IPv6 LLA. Okay? Like IPv6 GUAs, LLAs can be configured dynamically by us, as we saw a couple of slides previous. This figure shows the LLA is dynamically using the FE80 : with the prefix of 10 and the interface ID using the EUI64 process or a randomly generated 64-bit number. So operating systems such as Windows will typically use the same method for both a Slack-created GUA and a dynamically assigned GUA. So here, when you're looking at the differences between the two, the top one is, again, EUI64 generated. I know that because I can see FFFE right in between the IPv6 addresses. In the bottom, I just see randomly generated. I do not see FFFE, so that one is understood to be randomly generated. Okay? So FFFE is the defining factor here, as well as flipping that 7th bit from a 0 to a 1. Now, Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. By default, Cisco routers will use that EUI64 process for the interface ID on all the LLAs on IPv6 interfaces. So here is an example. Okay? So you see above you the original 7079.b392.3640. It again inserts the FFFE, excuse me, flips the 7 bits, and now instead of 7079, you have 7279. So IPv6 multicast addresses have the prefix of FF00 double colon 8. There are two types of IPv6 multicast addresses. There are well-known multicast addresses, and there are solicited node multicast addresses. Again, noting that multicast addresses can only be destination addresses and not source addresses. Source addresses are always going to be unicast. There is only ever one source generating a piece of information, regardless of how many destinations it is going to. So well-known IPv6 multicast addresses are assigned and are reserved for predefined groups of devices. There are two common ones assigned multicast groups. The first one is FF02:1. This is the all nodes multicast group. This is a multicast group that all IPv6 enabled devices will join. The second is FF02:2, which is the all routers multicast group. And this is a group that all IPv6 routers will join. So the all nodes is a packet sent. So within the all nodes, a packet sent to this group is received and processed by all IPv6 interfaces on the link or network. Within the all routers multicast group, a router will become a member of this group when it is enabled as an IPv6 router with IPv6 unicast routing. So when we do this command, as I stated, for DHCP services or Slack services, this is the command. So by telling your device to be unicast enabled, your device now, be it the router, can give out those GUA addresses. So now going forward, what I'm going to tell you, anytime that you are dealing with a lab that has IPv6 in it, automatically make this one of your basic commands. If I do not do this, and I do not have a server, then the end device will never get an interface ID and you will not have communication. So it is very important in the realm of IP6 routing that you tell the device to act and do unicast routing. And it is a global command. Now, a solicited node multicast address is similar to the all nodes multicast address, except that it is mapped to a special Ethernet multicast address. The Ethernet NIC can filter the frame by examining the destination MAC address without having to send it to the IPv6 process to see if the device is the intended target of the IPv6 packet. This replaces essentially that DAD process of neighbor discovery. Now, IPv6 was designed with subnetting in mind, although, frankly, there really is not a need for subnetting within IPv6. However, you have a separate subnet ID field in the IPv6 GUA that is used to create subnets if you so wish. The subnet ID field is the area between the global routing prefix and the interface ID. Okay, so the first, if you're going to subnet, now you see the first 48 bits is the global routing prefix. The next 16 bits is the subnet ID, and still the last 64 become the interface ID. So if you were to separate that out, or if you were to take a /48 and add the 16 bits, it would still be the prefix of 64. So when you splay this all out, this subnet ID is the 4th hextet. So look how easy it is here. Rather than doing all the bits and borrow and creating all this other stuff that you have to do in IP4, you simply start counting. And you get 65,536 subnets with 65,536 addresses. And all you're simply doing here is counting up. So again, even in IP6, you are starting with subnet 0 and going to subnet F, or all ones. Okay, starting with my all zeros. These all would be my ranges that I could use. And then my last network there. So the global routing prefix is the same for all your subnets. Only the subnet ID hextet is incremented. So again, as you see here, the 4th, octet. 1, 2, 3, 4 is where your subnetting happens. So the example topology requires 5 subnets, 1 for each LAN as well as for the serial link between them. The 5 IPv6 subnets were allocated with the subnet ID field of 0001 through 0005. So here in this instance, again, they're not going to use the 0 network, although you could. So they're not going to utilize it. They're going to go right to 1, 2, 3, 4, 5. Okay? Okay, do understand the double semicolon after those numbers, that's the compression of all zeros. So these are the network numbers. These are not interface numbers. Okay? To do the interface number, as an example, the very first one here. Again, this first one identifies the subnet. Okay, it is the 4th octet. It is very, very common for students to forget that you have to put the rest of the address. Would you not agree when I decompress this? I need 8 hectex of information. So it's simply not going to be :1:1. It's got to be :1 :1, or I'm missing some hextets. Okay, so do understand that. Lastly, when we go in there and configure, this example here shows that each of the router interfaces on R1 has been configured to be on a different subnetwork. And so as you're going to see, or as you saw in the lab, the previous lab you did, router to router, you do need your prefix. So in IP4, it is the IP address and the subnet mask. In IP6, it is the IP address and the prefix. If you simply type in the IPv6 address without the prefix, your device will tell you that you're wrong.